All right. Okay, this is a good volume. Thank you everyone for coming. My name is Eric Habyan. I'm a post-baccalaureate researcher at UConn. And I will be telling you something about how ionized gas allows us to have an idea about galactic evolution. And so here's an overview. Okay, it's a little cut off, but I'm going to talk about some background on some big astronomical ideas and where heavy elements come from. So first off, I'll tell you what a heavy element is. This is anything in astronomy that is heavier than hydrogen and helium. So it's oxygen, carbon, nitrogen, any of the molecule or any of the elements, atomic elements that make up our body, make up everything essentially that we interact with. And so we'll gain some insight on what this means. And where better to begin with than the Big Bang? The universe started with instant expansion with a soup of quarks and leptons. And initially, there was nothing at the moment of the Big Bang, there was nothing in the universe that we see on the periodic table. And moments after the Big Bang, we see here 1 microsecond, protons were able to form, and within, 20 minutes of the beginning of the universe, protons stopped fusing together, and we saw free-floating protons and helium atoms. And then, here we are today, 13.8 billion years after the Big Bang. We have galaxies, stars, and we can now look and observe everything that we see here. And we have these heavy elements being created. We have the initial stage of a star. At the beginning, we have a stellar nebula. And this can form, depending on the different amount of mass that's available, we can have an average star, something like our sun, which will then turn into a red giant. And then during this lifetime, once it's evolved, we have various processes such as nuclear fusion, which allow for the creation of heavier elements such as oxygen, carbon, and nitrogen. And when a star like this dies, in what we call a planetary nebula, we get heavier elements. And then in a similar process, but with a star that has more mass, we get something called a red giant that leads to a supernova. And this allows for elements like iron and gold to be formed in excess. And we see these things all over our planet, which means that the remnants of everything that we have on Earth were previously created in star formation and star death. And here we see an example of the periodic table, which shows where all of these elements came from. And so we can see hydrogen, helium was formed with fusion during the Big Bang, and then we see a lot of the secondary heavy element, or the primary heavy elements such as oxygen and carbon formed in the nucleosynthesis of large stars and moderately sized stars like our sun. And so, okay, now we have a basis about some astrophysical phenomena that we know to be true, that we can observe, and we have a good idea. There's some speculation about the Big Bang, but we won't go there. And now we can talk about some underlying physics. So I know we're at an observatory and we like to say astronomers, but I'm an astrophysicist, so there's some physics involved here, so you have to bear with me. And so I mentioned ionized regions, and so we have H2 regions, which in astronomy we talk about H2 being singly ionized hydrogen. So this is different than what you might normally hear in chemistry or biology. You hear H2, but H2 in chemistry and biology is referring to molecular hydrogen, whereas in astronomy, we're talking about singly ionized hydrogen. And this is a key feature, because when we talk about ionized gas, we get a lot of emission, sorry, okay, I don't know what's going on here. When we talk about an ionized gas, what is this? We get particles moving a lot faster at high temperatures. And when particles are moving faster, you have electrons, free electrons moving, and they start interacting with atoms. And here we see a hydrogen, so a single proton with a single electron. So this is neutral, and then the free electron comes, hits the electron off, and now we have H2, which is singly ionized hydrogen. So going back really quick, this is what we see in these regions. And so when this happens, we get what's called a collisional excitation, which is just an electron hitting an atom and a photon being emitted. Okay, what's a photon? Well, this is just light. This is what physicists call electromagnetic radiation. And this can be emitted in and we get a wide variety of frequencies and wavelengths. And so the research that I've been doing at UConn specializes in only a small fraction. So right here in what's called the optical, in the wavelengths of light that I can see, and you can see. And so one of the telescopes that we use to observe these H2 regions is called MUSE, which is part of the Very Large Telescope in Chile, and it has a wavelength range of 485 nanometers and 930 nanometers. And so we go back. This is right about from here, right in the green, to here in the red. And then a second telescope that we're using is what's called SETEL, and it is named in French, so I won't attempt to say the name of it. But it's similar to MUSE. It is what's called an integral field unit, and this type of telescope takes a mosaic. And so here we have 11 by 11 Archimedes observation field of view, and so this type of telescope takes a picture on the sky, and we can get very high resolution data from these types of telescopes. And so SETEL looks a little bit more into the blue, which is necessary for what I'm trying to do with my research. And so let me tell you about what I'm trying to do with my research, and then what this means in terms of the context of how galaxies evolve since the beginning of the universe. And so this is an example of something that I look at, and this is what's called a spectrum. And we essentially, when we take a mosaic of these regions, we get, or of the galaxy as a whole, we get to pick out what spots we want to look at. And in particular, we're looking at the H2 regions. So we get this, and we can't see the key here, but some of the emission lines. So if we go back to what I was talking about with when these electrons interact with the existing elements, and that photon is emitted, when it interacts with a specific element and it drops from an energy level, we see a very, very specific and known wavelength that is emitted from these elements. And they span all in the range that MUSE and SETEL are looking. And so I have here labeled, the purple is chemical abundance, the red is density, and the green is temperature. And so looking at these different emission lines is what we call them. These emission lines are the specific wavelengths that the atoms are emitting. And we can take a look at them, we can compare them to each other, and this allows for us to calculate those temperatures, densities, and chemical abundances. And so these are there's supposed to be 4. There's another one right over here that you can't quite see. That's called NGC 4535. But I'm looking at 4 galaxies in particular. And they're all nearby. Like I said, you need very high resolution data to look at H2 regions because in terms of galactic scales, they're fairly small. And so when I'm looking at this, we're able to calculate these chemical abundances, and this is what we see. And so you'll note this looks like a mess. This is a little intimidating when we first look at it, but what's going on here is not too crazy. We have the red line, which is the chemical abundance values that I calculated. And so, I didn't clarify this, but chemical abundance equals metallicity. And so metallicity is an indication of the amount of the amount of elements that are larger than hydrogen and helium. And so in astronomer talk, we talk about metals as anything above that threshold. And so I calculated this red line here, and this orange line in the background is an empirically derived method called the strongline method. And so the strongline method uses only the strongest available emission lines. And so this emission line in particular, this oxygen-dependent emission line, is very weak. And so we can't detect it, we can't measure it for galaxies that are outside of our galactic or universal neighborhood. And so we only calculate it, we can only do this direct calculation for nearby galaxies. And so the strongline method is an extension of existing direct calculations. And so here we see a bunch of different strongline calculations for varying types of, or for the same data. So we input the same data into different methods, and they produce a wide range of results, which is unfortunate and doesn't allow us to extend our known knowledge to other galaxies that are outside of our universal neighborhood and are further away. So my project is to look at these 4 galaxies, 3 that you can see, and and to try to calibrate a method that will allow for us to generalize these strongline metallicities to galaxies that are really far away. And so new data, such as the James Webb Space Telescope, will allow for us to look at galaxies that are formed very soon after the Big Bang, 700 million years after the Big Bang, which is unheard of previously. Hubble, you can't really see the James Webb's image here, but Hubble it's not able to resolve to the same resolution. It's not able to look into the red-shifted wavelengths that James Webb is able to look at. And so James Webb will allow for new observations to be made, and we'll be able to look into the past and see how elements have changed over time, see the different abundance ratios, and to better understand how elements have moved and dispersed. And if we can find that, we can see that elements at the beginning of the universe we're less sparse, then we can maybe confirm our model of the Big Bang. But if we see that there's the same amount of these metals at the beginning of the universe, then there's probably a new understanding that needs to be made about nucleosynthesis and how heavier elements came to be. And so yeah, that's my research, and that's it in the context of galactic evolution. Thank you. Yeah. Yes, this is, I'm doing, at the moment, I'm doing all of this at home. So, I can't quite hear you. Oh, okay, I see. So I'm part of a collaboration called PHANGS, which is physics at high angular resolution in nearby galaxies. And yeah, sorry, that's a mouthful. But they're the ones that get the funding and then subsequently write the proposals to access time on the telescopes and subsequently take the data. And then I'm lucky enough to be able to access that data and do these types of calculations on it. Yeah.
Could you explain a little easier as to how this data that you're taking is going to ultimately lead to some better understanding of what current theories of Big Bang and universal expansion?
Yeah. So previous studies, such as this one here, they're all, for the most part, either centered on only H2 regions in the Milky Way, which is, from a scientific standpoint, very biased. If we are only taking our data from a single source, that's not very reliable. But these galaxies, so we have a little bit of a variety here. On the left and in the center left, we have galaxy that's a little bit, they're similar to the Milky Way, and then here on the right, we have less of the spiral arms. And again, it won't be perfect. Our generalization to galaxies that form soon after the Big Bang won't be as good as we would have liked because we simply can't access them. But the building up the data to more H2 regions, to a more general catalog of H2 regions in different galaxies will give us a better understanding of how, give us a model that allows for more intuition as to what other galaxies might look like. And so that's why it's not going to be perfect, but it'll give us a stronger understanding because we can look back at the early universe galaxies and see these strong lines that are very, very strong in emission, and then similarly they'll have these H2 regions that we're looking at here will have the same emission lines. And based off that data, so things like H alpha, which is the singly ionized hydrogen, is prevalent everywhere. And these types of emission lines will hopefully scale better than the other studies that are only in the Milky Way. Hopefully.
You expect there to be less metals the further you can get reliable data for?
Yeah. So early universe, we would expect less metals to be present because, less elements that aren't hydrogen, helium, because there's been less time for stars to form and then burn that hydrogen, helium into heavier elements and then go supernova and disperse those elements elsewhere. There's been less time for that to happen, so we would expect to see less of those elements there. And if we can confirm that they're not there, then there's more leverage to say that our current understanding of the Big Bang and the standard model of cosmology is to say that's true. Oh, yeah.
When you were talking about studying the galaxies, you can only study galaxies that are basically in the local group? Is that what you were implying?
Yes.
That are close to
Yeah. Yeah, so these are all quite close to us. They're on a universal scale. Yeah.
Right. Thank you.
Yeah. What was that?
Is there a reason why all the ones that we can see that you chose to study are spiral galaxies?
Yes. So H2 regions. Oh my gosh, I'm sorry. That is an awful noise. H2 regions they're only found in galaxies that are readily star forming. And so this is due to the fact that they're gaseous regions. So when you have new star formation, there's just a bubble of gas. And so this gas condenses, and then a star is formed, and then there's still some remaining gas around H2 or around this star, and that's what we call an H2 region. And so,
Last question.
okay, and so this bubble is heated up. Sorry, where was I going with this? Yes, okay. And so in older galaxies, such as elliptical galaxies, there is not as much star formation, so you see less H2 regions, and so I can't study them because they're not there. And similarly, such galaxies as dwarf galaxies, they're all older and they're simply not there, so we can't perform the same analysis.
Thank you.
Yeah.
We have about 10 more minutes before the rains come, so we might protect our equipment and close down. And thank you for coming.
Thank you, Eric.
Thank
Yeah,
you.
thank you guys.